give some give some updates on what we've been doing here in terms of radiometer technology, in particular for air-sea flux measurement. And I guess well, a little bit about myself. So, as I know, a lot of people on here, but not everyone. I'm at the Jet Propulsion Laboratory. I've been here almost 20 years or so, and we're in charge of the group here that does microwave instrument science, so bringing science concepts to instrumentation and evolving technology to do more and better things for future missions. So I'll be talking today about some technology that we developed in the past decade that is now flying in space, and how we're using that to develop some mission concepts. Well, have developed some mission concepts, and how those will evolve in the future using new technology. So let me get right into it here. Okay, I trust you can see this. Let me know if you can't. Okay, so I'll be giving this on behalf of a large team that's involved with the COWVR mission. And also the butterfly team. There's a number of members of the butterfly team on this call, and for some of the science questions, you can always defer to them as well. And what I'll be showing here today is how we're working on some new radiometer technology that enables these this air-sea flux measurement from space. And what you're looking at there in the picture is the COWVR instrument. I'll talk a little bit more about that flying on the space station. So if you're not familiar with Butterfly, it's a mission that was conceived, I think, starting in 2016, specifically to measure air-sea heat exchange from space over the oceans. So this is sensible and latent heat flux from the ocean to the atmosphere. It was proposed to the NASA Earth Ventures Mission 3 call, which was during fun development time, because it was during the COVID year. So we were all learning how to do WebEx as well, writing a major proposal. So that was a good experience for everyone on the team. And we got a Category 1 ranking through that process, meaning it was selectable. It was one of 4 that were deemed selectable. However, NASA decided to go with a precipitation mission and allowed us then to kind of regroup and re-propose for the next time. So this team is still together, still working, and we're always open to new scientists on this team as well. So if you're interested, you can either get in contact with me or Caroline Clayson or Anish, who can get you connected with the team. So the original motivation for the Butterfly mission was that we really don't know a lot about air-sea interaction at small spatial scales. At large spatial scales, the atmosphere seems to influence the ocean, but at small scales, the ocean seems to force the atmosphere. Small scale eddies moving as fronts are moving across. You have a lot of large amounts of energy exchange at these small scales. And all of the existing flux products have pretty large differences and pretty large uncertainties at the small scales, just because of the way that they're derived from existing sensors that weren't really optimized to make this measurement. So if we want to really progress in this area and have data to constrain our coupled air-sea models at very high spatial resolution, we need very accurate small-scale air-sea flux measurements. And this has kind of a global reach. Models show us that as these storms or mid-latitude storms are moving across western boundary currents, they can be influenced downstream, and you can change where the precipitation may occur. So, as for example, a storm moving across the Pacific, you can have very large differences in impact when a storm hits, just from changes of a couple hundred kilometers, where you're going to have you could have severe flooding in areas or drought in other areas. And this is one of the motivations for really understanding this small-scale air-sea interaction, because it is can help improve predictability out past 5 to 7 days, maybe even getting past 10 days for improved weather predictability. Now, we know that the ocean is full of mesoscale features, and the atmosphere flows at a different rate than the ocean. So we really need to be able to measure these fluxes using a measurement system that is capable of instantaneous high-resolution measurements, because the existing flux products, the drawback of those is they're calculated with different data sets. Different data sets that may not have the spatial resolution consistent among all the products from, say, the surface in the atmosphere, or may not have the right channels that you want to derive what you're trying to drive, such as, say, near surface air temperature, near surface air humidity. And if you look at what you need to measure sensible heat and flux, you need the air-sea temperature difference, you need the air-sea, or the saturation temperature of the air and the air humidity, as well as the wind speed. And a microwave imager sounder is a ideal solution for this, because it can provide all of these measurements. If you combine a low frequency imager with a microwave sounder, you're now able to measure both surface properties and atmospheric properties, and that's kind of the basis for this butterfly concept, to do all of these instantaneously, very accurately, with high resolution. And this means that this mission kind of occupies a unique place in terms of its accuracy and its spatial resolution, because all of the existing flux products derived from space-based assets, they're nothing wrong with the products. It's just that they're using data sources that aren't quite ideal to make this measurement. There's not really that many sensors that are optimized to measure near surface air properties. Generally, the sounders, the microwave sounders that we fly, they were built decades ago using older technology, and were optimized for sampling the troposphere at as many levels as possible, and through the depth of the troposphere and the lower stratosphere. And because they used older analog technology, that means they had a very limited number of channels, and generally only have one channel that has any sensitivity to the near surface properties. So they're really suboptimal for measuring anything in the boundary layer. The other issue is that there's no one single sensor that can provide all-weather surface properties, SST, winds, with near-surface atmospheric properties, temperature and moisture. And there's none that really provided all at the same spatial resolution all at the same time. So when you combine multiple data sources and you're trying to reach high spatial resolutions where things decorrelate much faster, you incur a lot of errors just because of that data combination process. And then the other thing is there's not really that many data sets or sources of data for very high resolution all-weather SST. Infrared can provide high resolution, but in the storms where we see a lot of the most significant flux occurring, you really are blinded because of the clouds associated with storms, so you can't get high resolution SST under storms. So that's what this mission conceived, to address all of these shortcomings of existing flux products and actually make an instrument that's dedicated to measuring air-sea flux. And to give you an example of what we could do with such a mission, these panels here are showing outputs from a 2-kilometer WRF model, and this is total flux computed from the model in the upper left-hand corner of a storm moving across the northern Gulf Stream. And you can see that there's a very high flux, up to 700 watts per meter squared. And then the right panel here is just a simple experiment to show what if you were trying to combine two different data sources at high spatial resolution, but offset them in time. So let's say you measure the surface at one point in time, and then you had another sensor come over later and measure the atmosphere at another point in time. And here we're using a 6-hour time difference, which is kind of typical if you're combining different data sources from satellites. You can see that there's that temporal decorrelation, without any other measurement uncertainty, can cause flux uncertainties of upwards of 200 watts per meter squared, which is quite significant. Now, on the bottom panel here, we show what Butterfly can achieve. So these were full end-to-end simulations, including all of the sensor uncertainties, the retrieval algorithm uncertainties, as well as the resolution, sampling resolution. And this shows what you could achieve under this front. And here you can reduce the errors to just 10 to 15% or 15 watts per meter squared for the low end. And now we're able to actually capture the full scene of what's going on under these storms with an instrument designed to do that. And it doesn't get everywhere. There are still some areas of precipitation that the instrument, even at C-band, wouldn't be able to get beneath, and those are kind of flagged out here. But overall, it still does a pretty good coverage within the storm here. So what do we need to get to do this measurement, and what's enabling this measurement? Why haven't we been able to do it before with the past radiometer systems? The problem is that our current radiometer systems, there's a lot of microwave spectrum below 200 gigahertz, and you have to really operate below 200 gigahertz to see the surface or anything in the troposphere. Above that, you're mainly operating in the upper troposphere and in the stratosphere. But most of the existing sensors that are flying today use analog technology, where every additional channel comes at a pretty significant cost. So our current sensors really, it's if you could take the spectrum and take all the principal components and figure out the minimum set that you would need, minimum channel set that you would need to do retrievals of, say, surface temperature, wind vector, precipitable water vapor, and temperature and water vapor sounding. And they only measure about 8% of the spectrum below 200 gigahertz, but there's a lot more information content in the spectrum that we're leaving kind of undownlinked or unsensed. And furthermore, these sensors, you typically hear of imagers and sounders. That's kind of just a classification. There's no real need to distinguish between the two, but it's just kind of a historical and programmatic thing that some agencies are more interested in surface parameters and want to fly lower frequency instruments that are more optimized for looking at the surface. And then you have other organizations that are more interested in, say, numerical weather prediction and need temperature and water vapor profiles, and they generally tend to fly imagers and don't worry about the low frequencies that you would need for the surface. And what this means is that you don't really have any sensor up there that does both sounding and surface imaging, so they're not really optimized to measure air-sea flux. So what we can do now that we have newer technology, which I'll be highlighting here as I go on, is that we can now consider two things. One is digital technology that enables us to measure large chunks of the spectrum digitally, so that there's not really an additional cost per channel. You can just digitize the spectrum, and you can do that very cheaply and compactly compared to what the older technology would do. And then the other is that we need a low cost to do this type of mission in an Earth Venture class. You need a very low cost, small sat ready radiometer system that can combine both imaging and sounding in one architecture. And that's what the COWVR mission was intended to demonstrate. And combining all of these things, then you get the Butterfly concept, which operates from 7 to 200 gigahertz and is optimized for measuring these near surface parameters. And it does that by kind of operating in regions that no other system currently operates in, because they're the so-called window regions, or the shoulders here of the strong absorption lines. This is where all of the surface information is. Right as the signal transitions from being dominated by the surface to being dominated by the atmosphere. This is as you're going up the absorption lines. That is the particular spectrum. The shape of that spectrum, the nonlinear shape of that spectrum, is where all the temperature and humidity information is, and that's where this butterfly concept is optimized and intended to operate. So just a little bit about digital technology. If you've attended any microwave AMS or any talks recently, you probably heard the term hyperspectral. So that's kind of jargon, but what it means is a radiometer that has very high spectral resolution that can be configured digitally. So you sample the spectrum at very high spectral resolution, about 1 megahertz, and then you can form channels digitally and bring down more or less all of the information in the microwave spectrum, and that enables you to improve atmospheric sounding over the extent of the troposphere. But it also allows you to get into these window regions where before it would have been kind of expensive to have a lot of channels in these window regions that really only provide you information right at that surface layer. Because unless you have a specific mission to do that, you wouldn't otherwise deploy a sensor for that. But these technologies allow us to digitize tens of 20 up to 50 to 60 gigahertz of bandwidth and measure the nonlinear shape of these window regions where all of this boundary layer information is. So there's a number of technology development programs that are in work, and I'll talk a little bit about those. But now we have the technology to essentially bring down all of the information content that's in the microwave spectrum and all of this boundary layer information that was previously not measured from space, which allows us to get to the types of accuracies for surface air temperature and surface air humidity that we need to make this flux measurement. So that's essentially what the butterfly sensor does. Is it combines the COWVR technology, which I'll talk about, with this digital sounder technology, which allows it to be optimized to provide simultaneously sea surface temperature, wind speed, air surface temperature, and air humidity. And it can do this in a small mission using the COWVR architecture, which simply put, it's a way to reduce mechanical complexity at the expense of a little bit more complexity in the electronics. So it's a novel receiver design that most of the cost in these systems in these large imaging systems is in the mechanical part of the system, not so much in the radiometer. So what this does is it simplifies the mechanical design immensely and puts that all in the radiometer electronics, and you can then do things much more cost effectively in space. And the digital backend not only improves the accuracy, but also makes the sensor more robust to radio frequency interference, which I won't get into here, but that's an added benefit of that. And the one nice thing about this measurement, and it has a very nice flow down from the parameters that you want to measure when sea surface temperature and air to the different channel sets. So it's a very compartmentalized way of doing this, and through the butterfly proposal development, we did a whole airflow down, science traceability matrix, derived requirements, and so forth, and showed that this was all feasible to measure air-sea flux at about 13 to 14 meters per second, or about 10% above 100 meters per second for or 100 watts per meter squared for latent heat, or about 50 watts per meter squared for sensible heat flux. So what you're seeing here were the original butterfly requirements in the black lines, and then what we were able to show through simulation that we could achieve for all flux scales. So let me just get into the technology that's enabling for this. And one of the instruments that I mentioned, COWVR, is on the space station. And one nice thing about being on the station is you can get quite remarkable views of your instrument operating in space. And here's a recent picture of the COWVR sensor operating with Aurora in the background. So it's kind of one nice benefit of being on the space station as opposed to a free flyer. So some of the technology development programs I'm going to talk about, well, focus on two main ones today. One is the COWVR mission, which is demonstrating this architecture. So the COWVR part is how do we take a large aperture imaging radiometer system and put it into a small satellite and do that affordably. That's the COWVR part of it. The other part is how do we measure as much of the microwave spectrum, particularly in these window regions where you need to cover a lot of bandwidth to measure these air surface temperature and humidity properties. How do we do that cost effectively within the resources, the power, the mass, and the volume resources that are available in a small set? So there's a number of airborne instruments that we're working on that are developing fully digital software-defined spectrometers that can cover tens of gigahertz of bandwidth at very high spectral resolution. And then there's some future technology, which I'm not going to talk about here. This is maybe 5 years or so on the horizon for being ready for space. But these are photonic technologies that can measure even broader bandwidth. So now we're talking about hundreds of gigahertz of spectrum with one very tiny chip. And you do this by taking the microwave signal and upconverting into the optical. And then when you're in the optical, hundreds of gigahertz of bandwidth is really nothing. And being able to separate that into 50, 100, 200 channels is also something that can be done with some, say, on the waveguide grading, which is the chip that you're seeing down here in the bottom of the screen, which was recently delivered for a NASA project. But that's further down the road. So the two I'll focus on today are COWVR and the microwave sounder architecture. So what COWVR is, it's a new architecture for microwave imager, and as I mentioned, it takes all of the mechanical complexity and trades that for a little bit more complexity in the radiometer design and the radiometer electrical architecture, and kind of minimizes the overall cost of the instrument in that way. And because it was such a different architecture, before it could be adopted into the world of operational sensors, it first had to be proven. And it now, I'll show that here in a second, it now has reached the point where it's been in space for 2 years, and we've now shown that it is performing equivalently to operational imagers at about 20% of the cost. And that's quite significant when you're trying to do a small mission, or if you're trying to fly, say, a constellation of sensors to improve revisit time. So there's a lot of relevance here for NASA missions, and then in particular this mission to measure butterfly mission to measure air sea flux. So the COWVR instrument flies as a part of the STPH-8 mission, and with an acronym like that, it would certainly have to be a DoD mission. And so this mission is from the Space Force, and originally the Air Force, but now the Space Force. And what they're interested in is demonstrating new lower cost radiometer architecture. So they wanted to prove out the technology, prove out the COWVR technology. And then we also added in a microwave sounder that NASA had previously flown and proven. We had a flight spare sitting around, so we were able to incorporate that in the mission. So now we have a surface polarimetric imager with a atmospheric humidity sounder. So it's kind of like a light version of the butterfly mission. It doesn't include all the low frequency channels that you would need to measure, say, sea surface temperature and all weather winds, but it does kind of prove out this concept that you can do these types of measurements in a very low-cost mission. These two sensors, COWVR and Tempest, are on the station now. They've been there for 2 years, and they'll be there through at least the end of next year into 2025. And we are producing products from this, and they're distributed via PODAC. Right now, they're distributed to a limited list. We're working on getting full public approval from the Space Force to kind of open the gates. But if you're interested in any of the data, you can certainly get in touch with me, and I can work on getting you the access before we go full public release in January. Just a little bit of details about COWVR and Tempest. So COWVR is 18-channel, 3-frequency radiometer, fully polarimetric, with a resolution of better than 30 kilometers, about a 900-kilometer swath. So COWVR is providing ocean surface vector winds, precipitable water vapor, cloud liquid water, and precipitation rate. And then Tempest has 5 channels from 90 to 182 gigahertz. It's a cross-track imager. It's much smaller. It was originally designed for a 6U CubeSat, but it has about matching spatial resolution to COWVR, 25 kilometers at the low band and 13 kilometers at the water vapor sounding bands, and a little bit larger swath. And then when you combine these two, you can get some very interesting observations of surface wind vector with collocated precipitation or water vapor fields. So that's one benefit of having both of these. So COWVR has been, as I mentioned, working well. It's producing geophysical products that have been available now for, I think, almost a year now. And types of products that you'll see on the products are wind speed, wind direction, cloud liquid water path, and precipitable water vapor. And these are all simultaneous retrievals from the sensor, so you get all these at once. Another thing that we get from this, which the Navy and the Joint Typhoon Warning Center and the National Hurricane Center are particularly interested in, is the microwave imagery. The microwave imager constellation is dwindling as the sensors are kind of dropping out of the constellation faster than they're being replaced. Say severe storm imagery, this is tropical cyclone imagery, is one of the benefits that we can get from the COWVR sensor. These type of imagery products have been operationalized from the COWVR measurement from, I think, since July of 2021. So about a year and a half now, the Navy has been making these available to all the operational weather agencies, the TC products coming from COWVR. So I'll just talk a little bit about the validation results that we've gotten from COWVR, showing that indeed the sensor is performing as well as we expected. So the first here is just comparing. So the primary motivation for flying COWVR was wind vector measurement. It won't go into the full complete history here, but just the short version is that after NPOS, the DoD had at the top of their needs list wind vector measurement for their weather observation needs. And after kind of a few false starts in terms of getting a follow-on operational sensor, around 2012, they were looking for kind of small sat alternatives to make this wind vector measurement. And that's kind of where this COWVR idea was born out of well over a decade ago. And we started development of the sensor in 2013, completed development in 2016. We had a very long journey to get to space, and finally ended up on the space station in late 2020, started operating in January of 21. So the main thing that we wanted to prove out with COWVR is can this new low-cost architecture measure wind vector at the same level as WindSat, which was the prior passive polarimetric imager that the Navy had flown, and then also how well does it compare to, say, other sensors like ASCAT or other scatterometers. So a couple things that need to happen to make that possible. One is the COWVR sensor had to be calibrated to about a part in 1,000, which is challenging for any radiometer, but particularly challenging for this one because of the way that novel radiometer architecture was implemented. All of the things that make the legacy sensors easier to calibrate also makes them mechanically complex. So when you remove all that mechanical complexity, put it onto the electronics, it in theory would make it a little bit harder to calibrate. But we thought we would be able to, through careful characterization pre-flight and post-flight, be able to, and careful design, be able to calibrate it. And now, 1 year and a half, almost 2 years into the mission, we have achieved those objectives. The other thing that COWVR does, which is a little bit different than, say, WinSat or any other microwave imager, other than, say, SMAP, is it has 2 looks, so it can look forward and aft. And if you're familiar with wind vector retrieval, that is very important because you're measuring a sinusoidal signal on the ocean surface. Having observations at 2 different look angles gives you much improved performance over having an observation at 1 look angle. So the combination of having a forward polarimetric sensor with 2 looks really improves the wind vector retrieval compared to, say, WinSat, which only had 1 look. So what you're looking at here are the wind direction performance as a function of wind speed, and more or less any sensor is going to have issues at the low winds because of the signal to noise issue. But once you get above, say, 5 to 6 meters per second, we're doing better than 25 degrees, and doing much better better than meeting our objective, which was to do at least as good as WinSat. This is from NRL. They've done some independent confirmation of these results and comparing WinSat with ASCAT, with COWVR, and here they're comparing to NavGem, which is their numerical weather prediction model. And what couple things to point out here. So what you're looking at are different wind speed regimes here: 3 to 6, 6 to 12, and 12 to 25 meters per second. And then you're just looking at scatter plots of COWVR wind direction or ASCAT wind direction or WinSat wind direction compared to the NavGem. You see that COWVR kind of falls in between ASCAT and NavGem, not doing quite as good as ASCAT, but doing a little bit better than WinSat. And again, that's because of that 2-look geometry. And then the other thing you'll see is that kind of the pink points here, which are ambiguous solutions that were picked by the algorithm, that's significantly reduced for COWVR because of that 2-look geometry. Most of the wind vector solutions coming out of the algorithm are what you would call the first-rank solution, or the solution closest to the true one. So that's showing the benefit of that 2-look geometry. Then in terms of wind speed, we're doing better than meters per second, or about a meter per second or better for wind speed. So overall, the sensor is performing very well for its intended product, which is measuring wind vector. It's also providing precipitable water vapor and cloud liquid water consistent with prior sensors as well. So I'll just show some examples here. So this is some imagery from a storm, one of the series of large storms that hit the U.S. West Coast in March of, all winter basically of last year, or this year. So this is March 28th, 2023. There was a very significant system here moving on with an atmospheric river event, moving on to the coast of California, Oregon, and Washington. And I think this one was actually a bomb cyclone in terms of its intensity. So these are some imagery from COWVR showing the benefit really of having that combination of the surface and the atmospheric properties. So you can see the low pressure center over here. If you can see my mouse to the right of the image, with the water vapor kind of wrapping around the leading edge of the cold front, and you get all of this simultaneously. And then you can overlay the same thing on with clouds, and then again with wind speed, and providing the wind vector. The wind speed, I should note that COWVR really wasn't optimized to make measurements in rain. You would need lower frequencies for that, which the butterfly system is, but COWVR wasn't, just because it was a demonstration mission. It was just intended to can you make this measurement in any conditions, let alone rain. So we have to flag the COWVR measurements for the wind speed measurements, at least for areas of high liquid content in the atmosphere, but that wouldn't be a limitation of the butterfly system. These are some examples of some other Pacific storms. Kind of zooming in, you can see the wind vector solutions for this circulation center here in the Pacific, and then a little bit more intense storm just to the south of that. Then here's a southern hemisphere storm showing operational scatterometer product. This is from remote sensing systems, showing very similar features, kind of strong winds coming through the gap of New Zealand here, stronger winds wrapping around the South Island here, and then the circulation center to the north here of New Zealand. And then the one benefit of having COWVR and Tempest, which is the millimeter wave sounder, together, is that you can get precipitation. You can see precipitation in the atmosphere along with surface, what's going on at the surface. So this upper left image here is showing precipitation, convective precipitation from Tempest, which is the colored areas here. So the purple is the most intense precipitation, and then overlaid with the COWVR wind direction below, and you can see conversions right up to where surface conversions right up to where these strong convective cells are forming in the ITCC. And then you can do a similar thing here with the storm that I just showed previously, the one in the southern hemisphere just north of New Zealand. And now I'm overlaying the Tempest imagery, which is showing you where the most intense convective activity is happening in the storm. And you can see in the outflow region here, there's some small scale convection, and the surface wind field seems to be interacting with that. So these are all things that can be investigated with this combination of COWVR and Tempest, and would be in the future with a system like Butterfly. So let me just finish up here about with some microwave sounder technology, and I'm going to be highlighting two projects that are both funded by NOAA. One's an airborne sensor, and the other is a sensor that is a slightly more advanced version of the airborne one that's going to go on a balloon, a stratospheric balloon, and make measurements. So the first is this NOAA sounder that's going to go on the new G550 for tropical cyclone reconnaissance. What we've been able to do here is develop one of these software-defined fully digital spectrometers that can operate over the entirety of the absorption line complexes in the atmosphere, so around 50 to 60 gigahertz. Well, actually 48 to 72 gigahertz covers the entirety of the oxygen absorption complex for air temperature sounding, as well as being optimized for surface air properties, as well as the sampling around the 118 gigahertz oxygen line, which again gives you temperature information, and then sampling the wing and the window region of the water vapor absorption line at 183 gigahertz, which gives you that water profiling capability, but also improved measurements in the boundary layer. So this fits in the nadir port of the G550 under the floor. So it's a fairly compact instrument, and utilizes all of this new technology. And it actually wasn't really conceived to demonstrate any new technology. It's just that it's the most effective way to implement this type of system with the digital technology. So it just kind of came out of that. So the key piece of technology that's enabling for this instrument, but as well as a future air sea flux measurement, is a digital spectrometer. And this is when I first started working in this field, we might have been excited about 100 megahertz or 200 megahertz digital spectrometer. Now we're talking about 18 gigahertz digital spectrometers sampling at half megahertz resolution. So quite an amazing development of technology, and a lot of this comes from just technology developed in the commercial sector for say, communication devices and things like that. And we benefit in the science field by being able to use it for and configure it for our needs. But this the spectrometer, this 18 gigahertz spectrometer, so you would cascade a few of these to measure 20, 40, 60 gigahertz of bandwidth. And it's been fully characterized now in the lab and is showing very excellent performance. And we recently did a kind of an end-to-end test outdoors, just to show that it does indeed have the ability to sample the spectrum at very high spectral resolution. And what you're looking at here is the downwelling brightness temperature from the sky as you're going from 48 to 72 gigahertz. As you move along the absorption line complex here, the atmosphere is becoming more and more opaque, which is why the brightness temperature is increasing. And then eventually, when you get to the very strong absorption lines, which are up here close to 60 gigahertz, you're really just seeing the atmosphere right in front of you, the air temperature right in front of the system. And you can even see these small spectral absorption lines, which are just single lines that we can see quite well on either side of the oxygen absorption complex. So this was our crude calibration first light, but it is really exciting to see this. We're now able to have sensors that can bring down all of the information content in the microwave spectrum using this new technology. And I'll add that this the spectrometer only takes several watts of power, so it is really quite remarkable that we can do this now. And then I'll just finish with this. To mention this balloon demonstration. So what we're doing with the balloon demonstration, this is another NOAA project, is taking an existing instrument that's called HAMMER, which has channels that range from 18 to 200 gigahertz. And we're upgrading it with these new digital spectrometers to combine the low frequency imaging channels, 18 to 34 gigahertz, with continuous coverage. Spectral coverage from 48 to 72 gigahertz and 111 to 183 gigahertz. So this will be a nice demonstration of that ability to measure the near surface air properties with these spectral regions that no other sensor has really flown before. So this will be integrated on a balloon in late 2024. It'll fly in 2025 for 30 days over the oceans and land to acquire data over a variety of scenes. And then this information will be proposed or we'll use to give recommendations to NOAA and other agencies for future spaceborne sensors in the next decade. So I'll just finish up here with kind of where we've been and where we're going. So with the first version of Butterfly that was proposed to the EVM3, it was kind of the first time we conceived a sensor that was specifically optimized to measure air-sea heat and moisture exchange over the ocean. But we had to make some compromises at that time because some of the technologies that we wanted to be ready when we proposed this and starting in 2019, 2020, were not quite there, and we had to back off. So we originally wanted to fly a large aperture to get very high spatial resolution. And that would have required a deployable, but at that time, deployable reflector. But at the time, that technology wasn't quite ready. It was almost there, but not good enough to kind of pass the mustard for an Earth Venture mission. So we had to fly a solid reflector and fly at low altitude, which limited our swath width, so the amount of the storm that we could cover, or the amount of Earth that we can cover in one day, and also the spatial resolution. So we couldn't do much better than about 20 to 25 kilometers. We also had to use analog technology. The digital wasn't quite ready then. And that limited our spectral resolution and reduced slightly our accuracy for temperature and water vapor sounding near the surface. And we could only really promise scalar winds because at that time the COWVR architecture wasn't flown. COWVR wasn't flown yet, wasn't quite proven. But now things have changed, and that's kind of, I guess, the benefit of not winning the first time is you can incorporate new technology, incorporate the latest science, and so the new concept, the evolved concept, would now the reflector technology is mature. It's flying in space, and it's actually a part of the Earth Venture Incas mission, which was the one selected, and this will enable better than 15 kilometer spatial resolution over a much larger swath, so you can cover the whole storm up to 1,000 kilometers or maybe a little more. We do have these full digital spectrometers, so we're able to pull a lot more of the information down to the surface. And it actually does reduce cost because the older analog implementations required a lot of tuning, sensitive to temperature variation, so you had to do a lot more testing with the digital systems. It's just you're just copying these. They're not they're kind of frequency agnostic, and they're much easier to implement. And then we've also proven the wind vector measurement with the COWVR design, so we can also promise not only scalar winds but vector winds for the concept coming out. So I'll just finish with that. So we have a lot of new exciting technology that's been recently demonstrated in space or will be soon in airborne measurement, airborne systems. And you know, we're ready to deploy a system in space for a future mission that's really optimized for measuring air-sea flux. And you know, I should say that we're not in this alone. This type of mission is very complementary to others out there, such as Odyssey and other measurements that are really looking at this air-sea heat exchange. So I'll stop there, and I'm happy to take any questions and turn it over, I guess, to Sarah or whoever.
Well, thank you, Shannon. I'm sorry I missed the beginning. My internet shut down completely just at the top of the hour. This was fantastic. And yeah, questions from anybody? Tony has his hand up.
Hi, Shannon. Thank you very much for the comprehensive presentation, including some ongoing project that I wasn't aware of. So that's very informative. Question about the spectral window near 60 gigahertz versus the one near 120, both for temperature sounding. And both of them are used for the NOAA project, airborne. So what is the relative merit of these two windows for spaceport missions and for surface-based measurements, like you put on a ship or a buoy and looking up?
Okay, so yeah, the question Tony's asking about is, so you can do temperature sounding either at 50 gigahertz or 118 gigahertz, where you have 118 gigahertz, you have a single line. At 50 gigahertz or 60 gigahertz, you have a complex of many different absorption lines. So traditionally, most sounders have flown, have operated in 50 gigahertz. One has to do with somewhat the technology that was available at the time, but also because there's a lot more spectral features here, it improves the sounding in the upper troposphere. For the surface, you're really only using the wing here of the absorption line, where the signal crosses from being surface dominated to atmospheric dominated. And the information content in the wing is very similar between 118 and 50. You have a little bit more bandwidth to work with, so you can pick up a little bit more sensitivity at 50 gigahertz, but most of the error is dominated by the retrieval, not by the sensor noise. So you can use either. In Butterfly, we went with the 118 gigahertz because you can get more than double the spatial resolution by operating at 118 gigahertz on the wing of the 118 gigahertz line. You will be a little bit more sensitive to clouds, so that's another benefit of using 50. But overall, they're not particularly for surface sounding, they're pretty similar. And the same would go for upward sounding as well. It's pretty analogous.
Okay. Thank you.
If there are other questions, people should raise their hands or put them in the chat. But Shannon, can I ask about a particular case study? I think people have pointed out that Hurricane Otis that hit Acapulco, was it last month, was a big surprise because it accelerated so quickly. And one of the reasons the intensification was hard to catch was that it was cloud covered and the satellite data didn't catch it. How will a potential butterfly mission do with something like that hurricane intensification process?
That's a broad question.
Cloud covered conditions that totally failed so far.
Yeah. Well, I can speak at least for what in terms of the observational capability, saying what that would translate into in terms of improved predictability. It's probably more of a
there are many layers
question.
to this. Yeah,
I wouldn't be able to answer. But in terms of the observational capability, one of the things that we wanted to make sure we implemented for Butterfly was maintaining the low frequency channels, so operating in 5 to 7 gigahertz, and that allows you to kind of see through the precipitation and still get down to the surface. You're still going to have issues kind of in the higher in the high convection areas, where you have a lot of signal from the precipitation, but you'll certainly do a lot better than sensors that are most existing sensors that are either only go down to 19 or 10 gigahertz. There you're really kind of impacted by rain. So you do a little better, but any type of sensor in these complex environments is always going to have issues. Another benefit that you would have with this type of system compared to existing systems is the higher resolution, the spatial resolution. So you're able to kind of get in between the rain bands a little bit better and see what's going on at the surface. But yeah, it's a complicated problem.
Yeah. Other questions? Maybe one of the big pressing questions people have is how can the community as a whole support this?
Yeah, I mean that. I think. Well, certainly justifying the need for improved high spatial resolution ARC flux measurements in general is certainly the way to support this. Getting involved with the Butterfly team is another way. Where the original idea behind this Butterfly mission was to have it be open science, and that was before NASA really adopted, kind of went all in on open science. So all along the team has been very open. That the proposal is actually publicly available online. So if you're not familiar with it, you can go and read it. I think I provided the link here in this slide. It's really open to anyone that has ideas that wants to see something like this fly in a future mission, and that's really what it takes. Get involved.
Tony has his hand up, and then Rick.
Yeah, Shannon, so given that NOAA is having an airborne mission with the 50, 60 gigahertz, 100, 120, 160, or 180 hyperspectral channels, what do you think their future thinking is in terms of satellite with the similar frequency configuration? I know you cannot speak for NOAA, but...
It's always hard to tell. But the things that they're funding, the things that they're thinking about are, one is upgrading the any future sounder that they fly, upgrade it to some of these digital architectures where they can measure more of the spectrum. The term they like to use is the hyperspectral sounder. So they do seem to be be wanting to push into these digital architectures that allow you to sample more of the bandwidth. Traditionally, they haven't flown low frequency imagers. Other agencies have done that, the DoD, JAXA, and so forth. They did put out a call recently to look at architectures for combined imagers and sounders, but how that translates into what they fly into space and what they implement or decide they want to try to implement, it's a kind of TBD at this point. They have a very long horizon. They're thinking about things in the 2030 timeframe. So it's really hard to say. And technology is going to evolve so much by then anyway.
Right. Maybe a discussion for the next decadal survey. So yeah.
Yeah.
Thank you.
Rick, do you want to go ahead?
Yeah, hi Shannon. Really neat stuff. Digital spectrometry, it's just and hyperspectral retrieval is something else. Clearly, and it's unfamiliar too, but with respect to SMAP and SMOS, is there any I haven't seen the proposal, but for Butterfly, is the plan to keep the instrument on always as it circles the Earth?
Yep.
I mean, would you see
Yep.
over land as well? And if so, are there other communities that would support this? And then the final question is radio with SMAP and SMOS with the RFI interference and stuff for hyperspectral data. What sort of modeling would have to be done to help interpret the geophysical signals there?
Yeah, so yeah, it would be on all the time, and there are certainly a lot of applications beyond air-sea flux measurement that the sensor could be used for. From the cryosphere to land surface hydrology and so forth. For the mission, you have to really focus it on one, which is why it's focused on air-sea flux. But yeah, there's other communities that would benefit from the data. In terms of RFI, that's more of a problem at the frequencies that SMOS and SMAP operate, which is 1 gigahertz or 1.4 gigahertz. It is still a problem at the COWVR frequencies, and what we're implementing is a digital backend that's actually flying on SMAP, but it's optimized to do all of the RFI processing on board, and that would fly for every channel would have that digital backend. So you're more or less doing everything that is in your power to mitigate and guard against RFI. The benefit is that typically over the oceans, we don't see a lot of it because no one, you're not going to be wasting a lot of RF transmit energy broadcasting or doing anything over the ocean. So generally, we can work around any RFI that's observed on the ocean because it's going to be maybe in 1 or 2 frequencies, but not cover the entire spectrum. And that's what the digital spectrometer enables you to do by sampling natively on the instrument, even though you don't need 0.5 megahertz spectral resolution. If you sample natively at a 0.5 megahertz spectral resolution, these very narrow transmitters are very obvious. And what you do is you can on board look for signatures of the spectral emission and remove those before you combine the data and downlink it to the ground. So in principle, the data you get in the ground should be RFI clean. And you also, it's not like people are changing their transmit frequency all the time. Generally, if you see some type of RFI in a particular area of the world, you can characterize it and catalog it and make your algorithms a little bit more robust to the type of RFI that you're going to see in different areas of the world from the different sources, whether it be air traffic control radars or communication devices or whatever it is. So the digital technology is really what helps you kind of get around that and give clean spectrum to your retrieval algorithms.
Was that the reason for not going to lower frequencies at all, or?
No, the reason is the reflector. Once you go to low frequencies, you need a very large. If you look at SMAP, it's a 6-meter reflector. If you look at Zimmer, which is a mission coming up in the future, it has an 8-meter reflector. That is not really amenable to fitting in with a an Earth Ventures cost cap. You need to limit the reflector size to no more than about 2 to 3 meters, and there you're talking about resolutions that are 60, 80, 100 kilometers at those low frequencies.
Great. Well, sounds great. It's really interesting stuff. Thanks.
Well, thank you so much. We've gone slightly past the top of the hour, so we'll have to bring this to a stop, but this has been a really great discussion. Thank you very much. And thanks everyone for participating.
Thank you, Shannon.
Thanks, everyone.